Hey, everybody. So here is your lecture on section 3.1. All right. Let me get my stuff together. All right. So we've seen a couple ways of calculating E, if you remember, calculating the electric field given the charge density. For instance, you could, so let's say like calculating E, we've seen a couple different ways. So one way is like the kind of most general way is we have this big integral, right? 1/4 pi epsilon naught, and then we have the integral of rho of r prime d tau prime, and then there's this omega hat over omega squared. And we've seen how that can be, hard, even when you have nice symmetry like spherical symmetry, etc. This can be really hard. Sometimes we get even luckier and we can use Gauss's law. So there's this way. There's, if we're lucky, can use Gauss's law, but you've seen how limited the situations are that where you can use Gauss's law. Okay. And then, but maybe we could, it's slightly easier to get the potential, right? And then use the gradient. So we could get the potential and use E equals minus del V, where V can be written in terms of this integral, right? But the integral is slightly easier just because it's not a vector integral, so there's no omega hat up here, but this still can be terrible, right? So it's the charge density d tau prime over just omega, so it's slightly easier. Okay, so this can be not much better than the other one. Okay, so, and this also can be really complicated if you have like some conductors lying around, as you know from our previous lecture, section 2.5. You may not know rho since the charges can move, right? So in a conductor, charges can move. You might know the total charge Q. Great. So it really helps to have a differential equation form for getting V, because then you can just take a gradient, right? So if we can get a differential form, we've seen it, I've written it down before, and that's what we're going to concentrate on in this particular section. Okay, so we're going to concentrate on the differential form of for getting V. Okay, so this looks like this. Del squared V is -1/epsilon naught rho, right? And this was Poisson's equation. Okay. And with appropriate boundary conditions, which we always need, if you don't have those, you're out of luck completely. But if we have boundary conditions, this is equivalent to the integral, meaning we can use it to get V totally completely without having any problems. Not to say that solving differential equations is easier, but it tends to be easier than doing integrals. Okay. Now, often we're actually interested in finding V in a region in which rho is 0. Now, of course, rho is not 0 everywhere because there would be no potential if there was no charge anywhere in the universe. But you might be interested in a region in which you're outside of the charge distribution, right? In that case, our Poisson's equation, so if we have, if we are interested in a region outside of charge distribution, then we can solve a slightly easier differential equation. Del squared V is equal to 0. This is Laplace's equation. Okay. And in like Cartesian coordinates, what does this look like? I've written it down before, but let's just look at Cartesian. Del squared V, del x squared plus the partial derivative squared of V with respect to y squared plus another partial squared of V with respect to Z squared equals 0, right? That's what that equation looks like. And the solutions to this equation are called, these solutions are called, called harmonic functions. Okay, just so you know the nomenclature. Okay, let's just look at this in 1D, see what we can see. All right, so let's do Laplace's equation. Oops, that red. Oh, that's okay. Laplace's equation in 1 dimension. Okay, so this would just be d squared v dx squared equals 0. Okay, this has really easy solution because one, this v, so presumably v is only a function of x, right? There's no x, there's no y and z. So this means this really is just a regular derivative, d squared v dx squared equals 0. Easily integrated. In other words, I can integrate once. So I can say d ddx of dv dx equals 0, right? And if I integrate one, both sides here, so in other words, I would separate this out. So how would I do that? I would say d and then dv dx is equal to 0, right? And I can integrate one, oh, I'm doing this wrong. Give me a second here. I'm completely doing it wrong. Yeah. So let's just think about what functions when you take the second derivative do you get 0? Well, it's linear functions, right? So v of x must be mx plus b. Think about it. You take one derivative, you get m. You take another derivative, you get 0, right? All right. Now, we don't know what m and b are. Here's where boundary conditions come in. You have to have them, okay? If you don't have them, you don't have a solution. Yeah, okay, maybe you know it's linear. That's all you know. Okay, so let's get some boundary conditions. Let's just make some up here for this. So our boundary conditions, yeah, let's use a different color for that. So boundary conditions. And again, I'm just making these up, right? This is something that would be given to you. You have to know this ahead of time, right? You can't find the boundary conditions usually. Sometimes you can from some physics of the problem, yes, right? But somehow you have to get them either given to you or get it from the physics of the problem. All right, so let's have v equal 4 at x equals 0 and v equals, oops, sorry, bad. V equals 0 at x equal 5. Okay, well, this is easy. So now let's do the first one. So here, we'll do this one. So we have if v is 4 at x equals 0, so this means that b is 4. Okay, and that means that v of x is mx plus 4. Okay, now we got to find the next one, so let's do that in pink. So we have here, we have b is 0, so we have 0 at x equal 5. And so we have m times 5 plus 4, right? And so let's see. B0 at x equal 5? Yeah, okay, okay. Sorry, I think I messed up my boundary conditions when I was solving for them before. Okay. All right, so let's move, let's solve. So we have 5m is equal to -4, and so m is equal to -4/5. Yeah? Okay, so this means V of X is equal to -4/5 X plus 4. Okay, so now we have the solution. Now, how I got a different number in my notes. Yeah, doesn't make any sense. 5X. Yeah, I don't know. Who knows? Okay. All right. Okay. Maybe you'll figure it out and figure out if I made an algebra mistake. Okay. Sorry, give me 1 second. I just want to make sure because it's weird that I have something different in my notes. X equal 5. Yeah, just a little bit strange. Maybe I meant to say X equal 4. Yeah, I think I switched the boundary conditions around. Yeah, I think I did. We'll just keep this one. I think in my notes, it was supposed to be V equal 5 at X equals 0 and V equals 0 at X equals 4. Anyway, all right, never mind. Okay, fine. So, there are two things that we can write down about V in one dimension that actually generalize to 2 and 3 dimensions. Okay, but if we've seen how you solve it, how you can solve Laplace's equation 1D trivially, as long as you have some boundary conditions, right? You can actually get the full solution. All right, let's look at the two things that generalize to higher dimensions. Two things. Okay, so two properties that generalize to 2 and 3 dimensions. Okay, one. We're gonna use our you're gonna see how this is gonna generalize, but I'm gonna use 1D as the example. Okay, so V of X, so V at a point X is equal to the average of V of X minus A and V at X plus A for any A. I should have color coded this. For any A. Okay, so let's look at our example here. I'll do this in yellow. So, all right, so let's write that down a little bit. I'm going to write that down a tiny bit more formally. So this means that V of X is the average. So 1/2 of V at X minus A plus V at X plus A. Okay, so that means if you sit at a point, that point is just the value of the function at that point is just the average of these 2 points around it that are equidistant, right? Okay, so let's look at the example that we have, right? We have our solution. We had V of X is equal to -4/5 X plus 4, right? All right. Let's look at V of X plus A. Okay, well, that's going to be -4/5 X plus A plus 4. Let's look at V at X minus A. That's going to be -4/5 X minus A plus 4, right? It's a weird way of writing it, I know, I'm sorry. And let's look at the addition of these two things. So when we now do the plus, right? When we add these two together, obviously we get -4/5 X plus 4, but we get that twice, right? So let's do that. Right? Because the A's will cancel and you'll get 2 of these terms and you'll get 2 of these terms, right? 2 of these terms and 2 of those terms. And that's what you get. But of course, the average is 1/2 of that, right? So the claim is that V of X is 1/2 of V of X plus A plus V of X minus A, right? Well, it is because it'll cancel that too. 1/2 times 2, -4/5 X plus 4. In other words, just v of x that we had. Okay, but this property generalizes, as you'll see what that means in higher dimensions. Okay. Or you'll see how to write this average out in higher dimensions. Okay, that's property 1. Let's look at property 2. So property 2. Let's see, let's get a different color for that. 2. So we have v of x. This is an important one. It's a little hard to get your head around. V of x will not have any local maxima or minima except at the boundary points. At the boundaries, I should say just the boundaries, right? Because when we go to higher dimensions, boundaries are not points. Okay. In this case, it's very easy to see because you could say, oh, look, you know, our V is just a line, right? With an X and with a Y intercept of 4, right? So it hits here at 4, and then it has a slope of -4/5, right? So we go down 1, 2, 3, 4. I guess that's 4. Sorry, I'm not very equidistance. Down 4 and over 5. 1, 2, 3, 4, 5, right? And let's just go, yeah, like that. Okay, anyway, those 2 points. Okay. And we said it was 5 at x equals 0, if I remember right. Let's go back. I gotta go back, see what I said. No, it's 4, my bad. No, sorry, my bad. No, this is good. At x equal 5, b is 0. Okay, good. Right, and you can see that the minima is at the boundary and the maxima is at the boundary, but it's smooth, right? It's just a line coming down for in between those 2 points. Okay, this is a general thing. Now, once we get to 2 and 3 dimensions, it's harder to visualize, but we'll talk about it. Let's go to 2 dimensions. Let's see if we can go to 2 dimensions now. Okay, so we'll go to 2D. Okay, so we're gonna have d squared dx squared v plus d squared v dy squared, and we're equal to 0. Remember, v now is a function of x and y. Okay, so these are sheets. Okay, so we had a line, but these are sheets, like surfaces. And what do they look like? Well, there's a good example in the book, and I'm going to be really terrible at drawing it. But if you can imagine sort of cutting a cardboard box's top off, but not straight, so don't just cut it off like this. You're going to cut it off in kind of wavy pattern around the box, or right, some weird pattern. And then you stretch a rubber sheet across it. So if we look here, right? I'm really bad at drawing this kind of, oh boy, that's really bad. Okay. No, that's not what I want to do. Give me a second here. Okay, and then we have, you know, a box. Oh, wow, this is terrible. So we'd have like, you know, some wavy like thing that we've cut into this box. Right, and then you stretch a rubber sheet across here. Right? That's what the sheet would look like. Okay, now the height of the sheet will satisfy Laplace's equation. So that's what you would get. That's what it looks like. But they also follow these 2 properties that we talked about before, right? So let's go back and look at them. Oops, not 2 at a time. So we have 1, which is that the value of the function at a point is going to be the average of points around it. So let's look at that one. So this is condition 1. Okay, but we state this a little differently, right? So we have v at x and y at a point is the average of points around it. So in other words, if I have a point here, x, y. The points around it at a radius r around it, okay, like this. The value at xy will be the average of the points all around it in a circle. Okay, so we can write that as v of xy is 1/2 pi r. This tells me I'm averaging around the circumference, right, of v dl. This is the way you write an average of taking all the points along a circle. Okay, so it's the same idea as saying I'm going, A away on one side and A away on the other side, and I'm averaging those 2 points and I get the value in the middle. It's the same idea, right? Okay. Okay, so this is equal average v around circle. Okay, all right. The other property is harder to imagine. Okay, so let's go back to our other property is v of x will not have any local maxima or minima except at the boundaries. Okay, so let's go back. So you've got the sheet and here are the boundaries, right? So here in pink is the boundary, this wavy weird thing that you cut the box, right? This is the boundary. And the statement is that there are no minima or maxima inside in the yellow area. Okay, so when you stretch that sheet across, there's not going to be a dip down in the middle or something. So if you roll a ball across the sheet from maybe a high point over here, it'll roll all the way down to here. It's not going to settle somewhere in the middle. Excuse me. Okay, so that's harder to imagine, but that's the case. Okay. Now, let's remember that you can't solve this equation either without boundary conditions. So you need to know that boundary of that box, right? You need to know what the value of that wavy function is. So if we're thinking about this being like, uh, like y, so how high the boundary is, right? Versus x. It's a little hard to imagine because it looks like we have 3 dimensions here, but we don't. It's really 2, right? Okay, but anyway, you need to know what all the points are, right? As this kind of boundary goes up and down around the box. Okay, so you have to know that, otherwise you can't do anything. All right. Well, let's talk about a really interesting property of these equations in any dimension, and that is that the solutions are uniquely determined if you know V on the boundaries. So that's really great. That's very helpful. So, and I'll show you, we're going to do an example where it's just amazingly helpful to know that. So this is called the first uniqueness theorem. Okay, and this says the solution to Laplace's equation is uniquely determined. Oh, can't spell uniquely. All right, determined if V is specified on the boundaries. Oops, on the boundaries of the problem. Okay, so for example, let's say, here's our example. Let's say that we have a region, well, an enclosure of some kind. can think of whatever, it doesn't even matter what shape it is. So we have an enclosure. And enclosure. Okay, that just means that you've got a closed region, right? That a closed region that's completely surrounded by a conducting wall, by conduction material, superconductors. Okay, and there is no charge in the interior. Okay, so here Laplace's equation applies inside, right? There's no charges in there. We're not worried about the walls, except for the walls tell us something, right? The walls tell us because it's conducting, and we know that conductors are all equipotentials, right? So if you have a conductor, everywhere on that conductor is going to be the same potential, whatever that potential is. So we know at the walls, that's the boundaries of our enclosure. So on boundary, let's say that V is just some V0, right? We know it's got to be the same, but it's the same for all of the conductor. So think of it as let's just, for the heck of it, think of it as a sphere. So you've got this conducting sphere and you're looking inside, right? We want to know the solution inside. And we know that that whole sphere, if it's a conductor, is at a constant potential. So I'll just call it V naught, right? Okay, so now I know that V is V naught on the surface. That is the boundary of the space we're interested in, which is the inside. Okay. Well, since I know that V is V0 on the boundary, why don't I just make V0 everywhere inside? If I can think of that, right? The uniqueness theorem says that must be the one and only solution. So by uniqueness, V must be V0 everywhere inside. Right? That's what the uniqueness theorem does for you, right? Because you know, because it's a conductor, must be an equipotential, whatever that potential might be, right? And because of uniqueness, you can say, well, there's a solution in which everywhere inside, it's also V naught, which would allow for V to be V naught on the boundary, right? That must be the solution, because if I can think of that and it matches the boundary condition, right? It must be the solution. So it's really interesting, this kind of uniqueness. Okay, but okay, what if there is charge? Okay, what if there is charge? There is a corollary to this uniqueness theorem when we have charge. Okay, so let's look at that. Okay, so what if there's charge? What if there is charge? Okay, then we have a corollary. The potential in a volume V is uniquely determined still can't spell that. I don't know how that's spelled. Determined if two things. A, the charge density in V is specified. You got to know that. And B, not much of a different color there. B, the volume the value of V on the boundary is known. So in other words, you have your boundary conditions, okay? Okay, so that's the corollary if you have charges. Okay, but what about if we have various charges on various conductors, right? Remember our conductors? Things move around. These charges move around as soon as they get put in on the conductors, right? We may not know the charge densities, right? Because as soon as we put those charges on conductors, they move around. Now we do not know the charge density. Okay, so there's a second uniqueness theorem for that. Okay. All right, so if we have various charges on various conductors, okay, then we have the second uniqueness theorem. Okay, okay, so that is in a volume V surrounded by conductors and containing a specified charge density rho, okay? The electric field is uniquely determined if the total charge on each conductor is given. So that's nice. If the total charge on each conductor is given. Okay, so this is very useful. We're going to see a lot more of how this is applied once we start actually solving Laplace's equation and Poisson's equation in 2 and 3D, which actually we don't do until section 3 point. Let me think. I can't remember. So I think it's 3.2. Yeah. Anyway, so that's it for 3.1. We are going to I'm gonna actually double check something. So while you're just waiting for me to double check, give me a second here. Let's gonna double check something from the book. I gotta get this down. Give me a second here. Let's double check. Yep. So 3.2, we're going to learn a whole different method for doing E. Okay. And then in 3.3, we're going to start actually doing the work we need to do to be able to solve Poisson's equation and Laplace's equation in 2 and 3D in various coordinate systems. As you know, probably spherical will be the most useful. Anyway, that's all for now. And we'll see you for the next section.